More importantly, today is the day before the midterm. So, okay, it's okay. The midterm is going to be very easy. You're my good students because you actually showed up. So I'm very happy about that. And so I will, of course, just quickly go over everything that we've done so far this term. And you'll see really, in the end, we've only done a few things, you know? I mean, it seems like, oh gosh, every week we have homework and you have to do it. And it's brutal, right? Okay, but really, we haven't learned that much. And it's going to be very easy when you get to the midterm. So see, in fact, I'll try to do a problem that, at least from the derivative side, covers everything we've done. Or at least some portion of everything we've done. Today is just review. Very nice. Okay, so before we get to the derivatives, let's start off with what we started off with. I think I started off with, that's about the first thing I did in this course. After that, we did limits. Okay, so what was a limit? Right, well, we have all these functions flying around that we learned in pre-calculus. Okay, some of them are very, very nice. Some of them have little asymptotes. Some of them do some weird things. Right? We saw some functions with holes in them. Right? And a way to really talk about these functions and what kind of behavior they have is with the language of limits. So, for instance, you might have some function. It's proceeding along nicely, and then, oops, it jumps up. All right, so say that oops occurs at some point A, and say the value that this function should have taken on A was 1, and the value that the function actually takes on is 2. And then we define the notion of a limit, at least in an intuitive way. Right? But the way we did it was by defining first, what, a one-sided limit, and then using the one-sided limits to get the limit. So at first, I actually have to put a symbol up here. Right? I can put a minus, or I can put a plus. Okay, and the minus means I'm coming from the left side, and the plus means I'm coming from the right side, right? Because this is where the minuses live, and this is where the pluses live. Fine? What are these limits? Well, as I'm coming from the left side, right, we look at what this function is targeting, right? What is it trying to get to? What should it get to? And clearly, well, there's that little dot there at 1, so we say, fine, the limit is 1, right? In our analogy with military operations, okay, you're targeting, you know, the weapons factory. That's what it's supposed to be doing. Does it actually get there? No. If you fired, it would miss. But we don't care. We only care about what you were targeting. Fine, so this limit is 1. Right? And that's what this function is targeting from the left. From the right, it's targeting 2. It happens to hit 2, but we don't care. All we care about is what is it targeting. Okay, so that's that limit. And now we can talk about the two-sided limit. Right? And what is the two-sided limit here? Does not exist, right? Why? Because the one-sided limits do not agree. Okay? You have two generals. They're deciding who you're going to nuke. Okay? One of them says we need to nuke the first weapons factory. The other one says we've got to nuke the second weapons factory. Since they can't agree, they can't fire the weapon. Okay? So this does not exist. Okay. On the other hand, if we move this function down a bit so that instead of jumping, right, it just misses this point and jumps up. Okay. The limit from the left is still the same. Right? Still hitting 1. The limit from the right, however, is now 1. Okay? The generals now agree, so they can fire. They miss. Right? What did they hit? They hit 2. Okay, but we don't care, right? As far as the limit is concerned, we're happy that they could fire. Okay? And what did they agree on? They agreed on 1, so the two-sided limit is going to be a 1. Now, this is not equal to f of a. Okay? So this implies f is not continuous at a. Okay? So continuity meant not only do they agree on a target so that they can fire, but they actually hit the target. Right? Since this one doesn't hit the target, right, it actually jumps up to 2. It's not continuous at that point. Right? So our definition for continuity was, right, f is continuous at x equals a if the limit as x goes to a of f of x, right, well, it should exist, right? Meaning the two one-sided limits are the same, and it should actually equal, right, the value of f at a. Right? That's what the target is. Okay? The target should actually equal the value. So here it doesn't, but if we move this dot down, okay, then it would. Then it would be continuous. Okay? So that was our definition of continuity. Okay, now, we had a lot of fun playing around with these limits, right, trying to see how they evaluated. Now, with most of the functions we had in this class, they were continuous. And what continuous means is if you want to know what the limit is, you just plug the value into the function. Right? So as long as you have continuity, you can just plug it in. No problem. Okay, but where do we get a problem? Well, we get a problem, for instance, when we try to do things like the limit as x goes to a of x squared minus 4, x goes to a, x goes to minus 2 of x squared minus 4 over x plus 2. Okay? These are two very nice functions. They're polynomials, so this is a rational function. Right? Normally rational functions are continuous, except where? When the bottom is 0, right? That's how you get a problem in the domain of the function, right? A rational function. The only way you get a problem is if the denominator is 0. Okay, sure enough, right? This has a problem at minus 2, and so as x goes to minus 2, right? We can't just plug it in, because then we get a 0 in the denominator. Okay, fine. So this means it's not continuous at x equals minus 2, so we have to play a game. Right? What was the game we played? Right, well, you try to manipulate your function, right? You do some algebra to it. Okay? The first trick that you're always looking for is canceling. Okay? Can you factor out and then cancel? In this case, we'll be able to do that. Right? The top is x minus 2 times x plus 2, right? Using the difference of squares formula. We divide by x plus 2. We see on top and bottom you have x plus 2's. We're allowed to cancel because in a limit, we never actually let x be minus 2. Right? After we cancel, we're just left with the limit as x goes to minus 2 of x minus 2. Right? And now we do have a continuous function, right? There is no domain problem here. So we are allowed to just plug minus 2 in. And so we get minus 2, which is minus 4. Okay? Then we see some harder ones. Let's say we put an x over 3 here, and we'll do a square root of, let's say, x. What should we put in here? How about, I don't want to do that. Let's put that'll be fun. X minus, okay, x plus 1. Put a minus 2 down here. And what should we put on top? No ideas? Let's say, how about, what should we put? How about x squared minus 9? How about that? Does that seem like a good idea? You got to learn to work these backwards. If you can create these problems, then you can solve them. Okay, so what would I do here? Well, the first thing I see is I have a difference of squares, right? That'd be really nice. I just factor it and then cancel, but you know what you're going to get, x minus 3 and x plus 3, and there isn't one of those on the bottom. So what should I do? Multiply by the conjugate, right? So the factoring trick, you can immediately see, is not going to work. So the next thing in your your decision queue is, let's try multiplying by the conjugate, right? Which makes sense in this case. Okay? And why would you do that? Well, we know when you multiply by the conjugate, you're going to square terms, right? Which means square roots are going to go away. That could be good. So let's multiply top and bottom by the conjugate, right? Which is the same expression, but with a plus. Okay, so let's just leave the top as it is. Who knows what the right thing to do will be? And on the bottom, what's going to happen? Well, you're going to square this term and you get x plus 1. And you're going to square 2 and you're going to get 4. So you subtract 4. So this bottom part will be x minus 3. Right? So that's just the bottom. Now the factoring trick will work. Right? This x squared plus 9 I can break up. Let me rewrite it as x minus 3 times x plus 3. Aha! These x minus 3s will cancel. This is going to get rid of all my problems in the denominator. Right, so I'll just be left with x plus 3 times the square root of x plus 1 plus 2. All right, and now, with the possible exception of square roots, okay, there's no possible domain problems. Okay, what about the square root? Well, the square root will have a problem if you get negative numbers. But I'd be plugging in a 3, right? That's certainly not going to make this negative. Okay, so I can just plug 3 right in. Now we have continuous functions. So I get 3 plus 3 is 6. 3 plus 1 is 4. Square root is 2. Plus 2 is 4. 6 times 4 is 24. What up? Okay, very nice.
Professor, before you erase that,
Yeah.
over here, with the jump discontinuity there, the limit does exist and it's 1, but it's not continuous, or the limit doesn't.
That's right. So here the limit does exist, right? Because the targets agree.
Yep.
Okay? But it's not continuous because it doesn't actually equal the point it should.
Okay.
Right? So if you like, it doesn't hit the target.
Right.
I mean, it does, they target something they don't hit. So there's a lot of different things that can happen, right? One-sided limits could exist, and the two-sided limits don't. The one-sided limits might not exist, right? The two-sided limits could exist, two-sided limit could exist, and it not be continuous. Could be continuous, and then later on, not be differentiable. Right? So there's all sorts of conditions that get worse and worse here. Okay. Let's try to do an infinite limit. So I'm not being exhaustive of all the possible situations that could occur, but this is at least a flavor. Okay, let's look at this limit. Okay, now, you go into the math department, you ask this question of any of the professors, they're going to immediately look at it and say what?
3.
3! Excellent. You could be a math professor. Wonderful. Right? Why 3?
Because cancel the exponents are equal.
Yeah? Exponents are equal?
So it's a over.
So it's okay. So we had this formula, right, from the homework, right? We said, you look at the highest degree term, right? Everything else doesn't matter. You just forget about it. Cover it up with your hand. You say, I have 3x squared over x squared. X squared to cancel, you get a 3. What if it was the limit as x goes to minus infinity of minus 3x squared plus 2x plus 1 over x plus 2?
And greater than n.
Let's see. So the only thing that matters in this whole thing is the highest degree term. Okay? So, up here, right, this 2x plus 1, you can cross that out. This x squared is much bigger than this x, right? So this x isn't going to matter. Right? The only thing that's going to matter is this x squared. Okay? As x goes to minus infinity, well, when you square it, the minus doesn't matter. So this x squared goes to positive infinity. Then you multiply it by a 3, which doesn't matter. It still goes to infinity. But then you multiply it by a minus. So this will turn something going to infinity into something going to minus infinity. Okay? Now, if you want to write that out, okay, you don't want to just leave it to chance that you got the right answer, right, just by looking at it. Okay? What do? You start factoring things. You factor the highest power term out. Okay? When you do that, what do you get? Okay, up top, you're going to get x squared times minus 3 plus 2 over x plus 1 over x squared. And on the bottom, right? Well, I always like the idea of just factoring out the highest powered term in each one. So I get x and then 1 plus 2 over x. Okay. Now you know what's going to happen, right? All these things over x, those are going to go to 0. Right? Here you're just going to get a minus 3. On the bottom, what happens? Well, first you'll cancel. Okay, so you'll just have an x. And on the bottom, you have something that's 1, and then you have something that's going to 0. Right? So this is just going to be a 1 on the bottom, so you don't even have to worry about it. Right? So again, you're going to be left with, right? As x goes to minus infinity, the only thing left here is the x, the minus 3, over 1. Right? And of course, the over 1 doesn't matter. So as x goes to minus infinity, this function goes, ooh, look at that. What happened?
Minus times minus.
You went minus times minus, and uh-oh, it should be going to infinity. What's wrong? Yeah, there's something, right? The square is no longer there. So what happened? Well, yeah, of course, I mean, we figure the original formula should work, right? But, ooh, boy, now we're kind of worried. Okay, which one is correct? The first one is correct. Well, let's see.
No, second maybe.
The second one is correct, maybe.
Because minus infinity may be not included in the square, the minus.
Well, let's do this naively. As x is going to minus infinity, what's happening to the top? Right? Well, let's say we forget about the 2x plus 1. Right? Because we know that in the end this isn't going to matter a lot. Okay? And we can also forget about the x plus 2. Well, what's happening? Well, this term, right, as x goes to minus infinity, the x squared goes to infinity. You subtract, right, and then it's going to go to minus infinity. And on the bottom it's going to minus infinity. So it should be going to positive infinity. Right? So this is why you have to be very careful, right? It's easy to look at these, cover them up, and say, oh, of course, that's what's going on. Okay? But as soon as your x goes to minus infinity, then you have to be careful. Okay? So that's why I want you to write these things out.
So in the second one, where is it that the negative gets equal?
Where's what?
Like by factoring it, how do you, where is it that the negative becomes a positive?
So here, okay, in this one, right, it was easy to see, right? You have a negative on top, you have a negative on the bottom. It becomes a positive, right? Here, when you divide by x, what's happening? You're dividing, I mean, okay, well, actually nothing. Actually, the same thing is happening in both cases, okay? It never was negative, right? Here you have a negative times a negative, which is a positive, over a positive, so it goes to a positive. It's really the same thing as you have up here, only, I mean, here maybe because you have this x, right? But again, this is, if you think about it as x times x, and you cancel these, right? That was a negative and a negative. That's a positive also. So I'm only pointing this out to say there are two reasons to write these things down. One, you're less likely to make a mistake. Two, if you had just written minus infinity here, because you looked at it, and just like this one, you said, oh, okay, I know how these work, it's 3. Right? And you said, oh, minus infinity, I can't give you credit for writing down the wrong answer and having no work. Right? Even though you might be able to do a lot of these in your head, how do I grade it if you make a mistake and you show me no work? Okay, so that's why I show you this. Okay, but right, remember with all these sort of problems where you have infinite, your x going to infinity, right? The trick, factor out the highest powers of x, cancel, right? And write these things out. And remember, whenever you have an x in the denominator, as x goes to infinity, those terms go to 0. That's the whole point. Okay. Any questions about limits? Let me ask you a question. What's the limit as x goes to 1 from the left of 1 over x minus 1?
So 1 over 0, which is
Anybody want to throw out a guess? Colin?
Would be negative 1.
Negative 1?
Yeah.
Is that right?
Or no, because it's going to be very, okay, no, it's going to be negative infinity.
Negative infinity. Okay, so now I've heard negative 1, okay, which we said, okay, that's certainly not true, right? Because this denominator gets really small, so the fraction gets really big. Okay? Negative infinity or positive infinity. Those are the two suggestions that I've heard that seem reasonable. Is it negative or
It's
positive?
infinity.
It's not negative infinity. Colin's backing up. Well, what happens? If I put in numbers which are, what does it mean to come from the left? It means a number slightly smaller than 1. So if I put in a number slightly smaller than 1, all right, let's say 0.9. 0.9 minus 1 is some small negative number. Negative 0.1. Negative 0.1. Right? When x is smaller than 1, this denominator is always negative. It's a small negative number, but it's negative. So what's the right answer? Negative infinity. What is the limit as x goes to 1 from the positive side? Positive infinity, because now you have numbers slightly bigger than 1. So you say 1.1 minus 1. That's 0.1, but that's a positive 0.1. Right? So you're approaching infinity like this. Now think about what this function is. This is just, if you forgot about the minus 1, that's just 1 over x. Right? What does 1 over x look like? 1 over x looks like this. Okay? From the left side, it goes to minus infinity. From the right side, it goes to positive infinity. Okay? And what does this minus 1 do to the graph?
shifted.
It's a shift. Which direction?
Up.
Not up.
No.
Right? Because it's inside the function. It's not kind of outside and tacked onto it, right?
Left
So it's a
or
horizontal shift.
left or right?
We'll go left or we'll go to the right?
Right.
Go to the right. It's a negative 1, right? So to normalize it back to 0, right, you have to put in a 1. Okay, so 0 would go to 1. Okay, so this whole graph gets shifted over, but it doesn't change the limits at all. Okay, this would be the same as if I put the limit as x goes to 0 from the left of just 1 over x. Okay, which is again, right, or up. Right, and from the right, going up this way.
So always constant over infinity or negative infinity equal to infinity or negative.
Say again?
Constant over infinity.
A constant over, so over, okay, so if you have a constant over something going to 0, that will go to infinity. If you have a constant over something going to infinity, that will go to 0. Okay, and you think about it as if you have a pie, right? Nice, or a piece of cake. Okay, if you divide it up into more and more pieces, what happens to the size of the pieces? They get smaller, right? And as the number of pieces goes to infinity, the size of each piece goes to 0. Right? And as the number of pieces goes to 0, well, okay, now you have a problem because you can't have an infinite cake. Okay, it doesn't make any sense that way. Okay, but it's still the case, right? As these denominators go down, okay, the whole fraction goes up. Right? And as the denominators go up, the whole fraction goes down. Okay? Any questions about limits? No? Okay. Let's do some derivatives. So let's quickly write out everything we've learned about derivatives. And by everything, I mean some small subset. I want you to believe that it's not so much. So okay, first we define the derivative. Okay, so we had this nice definition, right? If you had some function which was differentiable, right, which is just going to mean that the limit I write down exists, okay, then the derivative is equal to the limit as h goes to 0, f of x plus h minus f of x over h. Okay, fine. This was our definition. Okay, you looked at this limit, and you said, okay, if this limit exists, then it's differentiable. If it doesn't, it's not differentiable. Okay? We were able to prove that if this limit is going to exist, i.e. if this function is differentiable, then what do we already know about the function? It's continuous. Excellent. Okay? So there's our derivative. And then we tried to actually apply this limit to functions to find the derivatives of those functions. And we decided that this was a lot of work. And so we better come up with some rules that will make it so that we kind of automate the process without having to look at limits anymore. And so what kind of rules did we come up with? We came up with, right, this sum or difference rule. Right? We just said the derivative of a sum was the sum of the derivatives. Same thing with difference. Difference meaning subtraction. Right? We have linearity, which actually includes sum and difference, but I'll just use it to say we can pull constants out. Right? So this one says f plus g prime is f prime plus g prime. This one says a constant times f prime is the same as f prime times a constant. Okay? We proved the power rule, which said if you take x and raise it to any real number, the derivative is just that real number times x to that real number minus 1. Then we learned the product rule. And this said that if you have two functions and you multiply them and take the derivative, that you had, well, it wasn't just the product of the derivatives. You had this nice formula that is f prime g plus f g prime. Okay, we had the quotient rule, which said f over g prime was low d high minus high d low over the low squared. Okay, we have the chain rule. It said if you have a composition of functions and you take the derivative, then this is f prime of g composed times g prime. Right? Okay, so these were our kind of working rules. And then we had a whole bunch of functions that we looked at. We had trig functions. We have the inverse trig functions. Okay, these are the arc sines and arc cosines and so forth. We have the exponential functions, right? A to the x, e to the x. We have logarithmic functions, right? ln, log base 2, log base 5, whatever. Okay. We have the hyperbolic trig functions. Maybe I'll write those as trig h. Okay. And then, of course, we have the inverse hyperbolic trigs, but I already promised you I won't put any of those on the exam. Right? Okay. So that's all we did, right? We just learned, I mean, there's a couple tables that go with these, right? But we saw, for instance, that trig functions and hypertrig functions, the derivatives are almost always the same, right? Just with h's added. The only difference is with cosine and secant, you have to add a minus. Right? We also saw that with trig functions, if you only knew the sine, the tangent, and the secant, you could get the rest, right? Just using the law of co. Okay? Every time you put a co into the function, you have to add c's to the derivative and a minus sign. Okay, fine. That was easy. Right? We saw the derivative, for instance, of if you had a constant a greater than 1, raised to a variable, the derivative was a to the x ln of a. For log functions, right, you did the derivative, say log base a of x. This gave you 1 over x times ln of a. So this is not so hard. Okay, just a few things to remember. Okay, so now let's try to write down a problem that's going to use everything.
Excuse me.
Yeah.
In this one, we're gonna shift it to white.
Yeah.
And what about the second one?
This one?
Yeah.
Everything. It's all, I mean, this is
Shifted to the.
everything gets shifted to the right.
To 1.
Yeah, everything has to get shifted to the right. So this has to. So if that's 1, right, everything's going to get shifted over to 2. So it's now going to like that, and then this thing has to get shifted over from 0 to 1. So it's going to like that. Everything's well. It should shift very nicely. This is not graphed very well. But everything has to shift over by 1. We'll graph. Okay, so let's try to compute the following derivative. How about sine of x over x squared plus 2 times, let's see, let's put a 3 here. How about log base, I like 2. Log base 2 of x minus 3 squared. Okay, let's see, what else do we, okay, we have sums, we have differences, we have linearity, we have a power rule, we have a chain rule, we have a product rule, we have a quotient, good. Okay, we have trig, we need an inverse trig. Okay, so I'll use our, say, arctan. Let's see, what are we missing? We have a log, we need an exponential. Okay, so let's do an exponential of, how about hypersecant of x? Okay, so let's see. So there's a sum rule in here, right? There's a difference, there's a sum. Okay, so we got that. There's a linearity because there's a 3 in the front. Okay, there's a power rule, right? We're going to have to use that here. There's a product rule because these two things are multiplied. There's a quotient rule, right? Because we have a quotient. There's a chain rule because you have a function of a function. Let's see. You have a trig because you have a sine. You have an arctangent, so you have an inverse trig. We have an e, so there's an exponential. We have a log base 2, so there's a log. We have a hypersecant, so there's your hyper trig function, and we don't care about that because we're not going to do it. Okay, so this example has everything. Okay, let's make some room. In fact, I'll move this up. Okay? All right, let's do it. Let's try to work this left to right. I mean, first thing you do, of course, is you look at it and say, okay, is there anything simple I can do? Do you see anything simple you can do? Tom?
You could break up, I guess, the first two terms as f of x times g of x and find the derivative of both.
Absolutely, right? Okay, so here you have a function, right? You might call this f and you might call this g. And that tells you you're going to have to use what rule? Product rule, right? Now, before we go on, look at this function a little closer. Right? I have a log of something to an exponent, right? And logs turn exponents into multiplication. So it's going to take this 2, and it's going to move it out to the front. And where does it go from there? Well, I can move all the way out to the front, and this automatically becomes a 6. Okay, so that's the first thing. So that'll, you can see that's actually going to simplify things a little bit. Yeah, okay, so that's nice. Okay, so we're going to have to use the product rule here. Okay. So we know what it's going to be. It's going to be 6 f prime g, right, plus f g prime. Minus, okay, now over here, what if we, let's see, how about we call this function u? Then what's going to happen? It's going to be the derivative of arctan of u. And what's the derivative of arctan? Good thing to know.
U plus 1 plus e.
1 over derivative
Square root of x.
arctan of x, 1 over 1 plus x squared. Okay, good thing to know. Okay, so this is going to be 1 over 1 plus u squared
Derivative of u.
times the derivative of u, right? Because I have to use the chain rule on this thing. Okay, so we've written this out. This is very, this is kind of nice and neat, right? We didn't write out this long, long expression that we get lost on, right? We just wrote it down in nice symbols. Now let's just decide what all these derivatives are. Okay, so f is sine, sorry, I should really say f of x, is sine of x over x squared plus 2. Okay, so what is the derivative going to be? Okay, well, what rule am I using right off the bat?
Chain rule.
Chain rule, right? Derivative of sine is cosine. Okay, and then I just have to put this right back in. Every time I use the chain rule, I do the same thing. Derivative of the outside, evaluated at the inside, times the derivative of the inside. Okay, now what do I have to do to find the derivative of this?
Quotient rule.
Quotient rule. Okay, fine. So, low, d high, derivative of x is 1. Okay, no problem. Minus, okay, high, derivative of low. What's the derivative of x squared plus 2? 2x. Okay, so I just get a 2x squared here. Over the bottom squared. Okay, that's not so bad. Okay, so we figured out what f prime is. Okay, now we need g prime. Okay, well g is log base 2 of x minus 3. So what's g prime?
1 over
1 over
X minus 3.
x minus 3
Natural log of 2.
times the natural log of 2, right? If this was ln, I'd be done. But with log base 2, I have to throw in an ln of 2. Times 1, right? Because I multiply by the derivative of x minus 3. But of course that's 1, so I don't have to write it. Okay, cool. We have the f prime, we have the g prime. All right, now we just need the u prime. So u is e to the hypersecant of x. What is u prime equal to? Right? Just the same thing times the derivative of hypersecant. What's the derivative of hypersecant?
minus 10.
What's the derivative of secant?
Secant.
Secant tan, right? Now with the hypers, it's always the same thing, right? Except with cosine and secant where you have to add a negative. Okay? Those are the only exceptions. With cosine and secant, when you go to the hyperbolics, you have to add a negative. So this is times, okay, well, if it was just, if you didn't have to add the negatives, this is what it would look like, right? Secant tan with the h's. But because it's secant, you have to put a negative out front. Okay, so cosine and secant, when you go to the hypers, those are the only exceptions. Those you have to pick up a negative. All the rest of them, they're the exact same derivatives with h's added on to the end.
So cos, you said cos?
Cosh?
I have to add negative.
When you do the derivative of cosh, right? If it was just derivative of cosine, it would be minus sine.
Yeah.
But derivative of cosh is sine.
Yes.
Okay, so you have to add the extra negative, so it becomes negative negative sine or just sine, okay, with the h, so sinh. Okay. And tangent, right? What's the derivative of tangent? Right, so what's the derivative of tanh? Sech squared, right? It's just the same thing, but you add the h. Okay? All right, and the only thing you have to remember is if it's cosine or secant, and remember secant is just 1 over cosine, so it's all about cosine. Right? If you have a cosine in there or a secant, you have to put in the minus sign. That's the only exception. Okay. Now, one could put this all back into this formula. One should or one should not. I say on this exam one should not. Okay? Here we have written down everything. Okay? We have a formula, and then I tell you, right, what each unknown piece in the formula is. Okay? I tell you what f is, I tell you what f prime, g prime, u, and u prime. Okay? Anybody who wanted to plug it in could. Okay? But you've done all the work, you've shown everything, this is perfect, move on to the next problem.
Really?
Absolutely. Well, what's the point? You know, in computer science, you know, they break everything up into these little modules. Right? It's object-oriented programming, right? You do little pieces of the problem in different places. And in math, that's just as good an idea. Okay? If somebody really wanted to write out this long expression, they could, but what's the point? Right? You've done the work, it's there. There's no sense in just killing yourself. Odds are you'll make a mistake copying it. It's not your fault, it's human nature.
What about arctan?
This is arctan. Yeah? Okay, so where was that? That was in here, right? The derivative of arctan became this, 1 over 1 plus u squared, times the derivative of u, right? So we had to use the chain law. And is it... So this problem has everything we've done in it, right? As far as derivatives go. I mean, okay, there's the other trig functions, right, that you have to memorize. Okay? But using those, I mean, you just have to know what those formulas are, right? Using them, it's the same as just any other function. Okay? So if you can do this one, you should be able to do just about any derivative I can put on the test, right? Okay. I've gone over time, so let me stop here. It does end at 10:47, is that? Or 10:45? Oh, 50, okay, I have 3 minutes to remind you about implicit differentiation. Good, good, good. Okay, so let's say you have some equation of the form, let's say e to the 2y times x plus sine inverse of x squared minus y. Okay, and we'll say it equals 0. Okay, so it's some implicitly defined function, right? Implicitly meaning I'm not giving you the function, you know, y equals a function of x. Okay? And I want to know what is dy dx. Okay? So dy dx is, okay, now I have to warn you, if you ever show this formula to any math professor who knows what they're doing, they're going to laugh at you because it's not actually precisely correct. Okay, the ideas are in there, but I don't want to go into the whole definition of partial derivatives, so don't worry about it. But there is a problem with it. Namely, I'm dividing two verbs here. You can't divide verbs, you can only divide nouns. Okay, so remember the way we did this, so we put down a minus, then we go through and we differentiate this top expression here, right, with respect to x, meaning we treat y as a constant. Okay, it's just like a 6. Right, so e to the 2y times x. Well, e to the 2y is a constant. So it's like a 6, 6x. What's the derivative of 6x? 6. What's the derivative of e to the 2y times x? E to the 2y. Okay, plus, okay, we have arc sine of x squared minus a constant. Okay, so we need to know what is the derivative of arc sine.
1 over
1 minus x squared.
Okay, 1 minus x squared, but here the x is actually this inside bit, right? So I have to put x squared minus y squared times what? I have to multiply by the derivative of x squared minus y, which is? Dos X by 2x, right? The y is just a constant. Okay, fine. Divided by, now I do the whole derivative again, but I treat x as a constant. Okay, so now x here is a constant. So what's the derivative of e to the 2y times a constant?
X e to the 2y
X
times 2.
e to the 2y, right? Because the derivative, the x just stays there. The derivative of e to the 2y is e to the 2y times
2.
the derivative of 2y, which is 2. Right? You have to use the chain rule. Okay? Plus, now we have to do the same thing. We have arc sine of x squared minus y. The derivative of arc sine is still 1 over the square root of 1 minus the input squared. Now we have to do times the derivative of x squared minus y, where x is a constant. Is it 1? Okay, imagine if this x squared was, well, if it's a constant, it can be any constant. So let's let it be 0. So you have minus y.
1. 1.
What's the derivative of minus y?
Minus 1.
Minus 1. Okay, now you could fiddle with this a little bit, make it look a little nicer, but don't worry about this. Okay, so it's very easy. Just write down your answer, right? And just remember to write down the pseudo formula. Pseudo because it's not exactly correct. Gives you the right answer, but it's formally incorrect. Okay, so I have office hours today, 1 o'clock. So come on in and see me if you still have questions. Good luck tomorrow. Bon chance. How do you say it in Spanish? What?
Buena suerte?
Buena suerte?
I think so.
For good luck? I just learned how to say tengo hambre. Yeah.
Can I ask you a question?
You may.